In this lecture, we briefly explain how to find the derivative of powers of x. We can expand expressions like x plus y to the fifth power using the finite version of the binomial theorem, often called Pascal's triangle. As an example of the binomial theorem or Pascal's triangle, we're going to compute the derivative of x to the fifth by the definition of the derivative. We need to compute the average rate of change, f of x plus h minus f of x over h, and then take the limit of the average rate of change as h approaches 0. Note that here, since f of x is x to the fifth, f of x plus h is x plus h to the fifth, which is 1x to the fifth plus 5x to the fourth h plus 10x cubed h squared plus 10x squared h cubed plus 5x h to the fourth plus 1h to the fifth. In this expression, the power on x keeps dropping by 1 while the power on h keeps rising. And most importantly, these numbers 1, 5, 10, 10, 5, 1 come from Pascal's triangle. So the average rate of change then is this expression on top minus x to the fifth all divided by h. But the x to the fifth will cancel out. Then the h's will cancel out of the denominator, so we get an expression without a denominator. And then we can plug in h as 0 so that our limit becomes 5x to the fourth. Again, let me go back and just repeat this. There's the average rate of change, f of x plus h minus f of x over h. When I do my computations with Pascal's triangle or binomial theorem, here is x plus h to the fifth. We subtract off x to the fifth. My x to the fifth will cancel out. I'll get an expression now in which every term in the numerator here has an h in it. We have an h on the denominator. Those will cancel. Now I have an expression over here on the right without any denominator. So now I can plug in 0. We get 5x to the fourth. Where did this 5 come from? It came from this first 5 up here in our expansion. In the fifth row of Pascal's triangle with entries 1, 5, 10, 10, 5, 1, all that really mattered in the end result was that second entry, that 5. And this is true in general. If we work with Pascal's triangle, we discover that the derivative of x squared is 2x. Where did that 2 come from? Pascal's triangle. The derivative of x cubed is 3x squared. The 3 was the second entry in row 3, and so on. If we work through a number of these, here's what we get. If my function is x squared, the derivative is 2x. If my function is x cubed, the derivative is 3x squared. X to the fourth, its derivative is 4x cubed, and so on. In fact, if we're careful and look at negative powers of x, like x to the minus 1, work out the algebra, we can get that the derivative is minus x to the minus 2. Here are some other examples that do not use Pascal's triangle. The derivative of x to the minus 2 is minus 2x to the minus 3. In fact, we don't even need to have integer powers. If the power on x is 1/2, the derivative is 1/2 x to the minus 1/2. If it's if my original function is x to the minus 1/2, the derivative is minus 1/2 x to the minus 3/2. There's a pattern throughout all of this. We are pulling down the exponent, this 2, 3, 4, 5, whatever the exponent is, becomes the leading term in my expression. Even if the exponent is 1/2, it becomes the leading term in my derivative. And then the new exponent, 1, 2, 3, 4, is the old one less 1. So instead of a 2, we have a 1. Instead of a minus 1, we have a minus 2. So our formula for the derivative of power of x, the derivative of x to the n, is n x to the n minus 1. The old exponent comes down, and the new exponent is the old one minus 1. This nicely agrees, by the way, with our belief that the slope of the line f of x equals x should be 1. Y equals x has slope 1. And if I think of x as x to the first power, then this pattern would say that my answer ought to be 1x to the 0, and that's 1. So we can even apply this result to the equation for a line. These results are collected into a formula sometimes called the power rule. The power rule says that if you have a fixed real number n, then the derivative of x to the n is nx to the n minus 1. This is our first example of a derivative formula, a formula that, given the original function f of x, will tell us the derivative or the slope at every point on the curve. We will collect these formulas in the second part of our first semester calculus course.